Hello everybody. So today we'll solve a problem on a simply supported beam which is of span 8 meter and it is subjected to an UDL of 50 kilonewton per meter including the self weight. Means this 50 kilonewton per meter includes both the dead load, that is the self weight of the beam, as well as the live load. Okay, so dead load plus live load is 50 kilonewton per meter. Okay, so we'll design this beam to resist flexure and shear. Okay, so first we'll design for flexure, or you can say bending. First we'll design this beam to resist flexure or bending. So as you know, to resist this bending, we have to provide the longitudinal reinforcement along the length of the beam. Okay, so first we have to calculate what will be the maximum bending moment for which we will design this beam. Let's say this is the simply supported beam and length is 8 meter, which is subjected to and loading which is equal to 50 kilonewton per meter including the self weight of the beam. Okay, so if you draw the bending moment diagram, it will be like this. So at the center of the beam we will have the maximum bending moment. So we have to consider that maximum bending moment to design this beam for flexure. So what will be the maximum bending moment at this point? This is the beam is subjected to UDL, so this will be WL square by 8. So the maximum bending moment for simply supported beam subjected to UDL, that is WL square by, this L should be L effective, WL square by 8, which is given, this L is given 8 meter, and W, this is W, total loading, it is 50 kilonewton per meter, length is 8 meter. So if we calculate, this will be 400 kilonewton meter. Okay, now we have to consider the safety factor. So we will calculate the factored bending moment. I am multiplying the factor of safety, that is 1.5 for concrete. So this will be around 600 kilonewton meter. Okay, now we will find out what will be the required depth to resist this much amount of bending moment. Okay, by considering it by considering the beam as a balance section. So as per the code, for balance section, what is the expression for bending moment, ultimate bending moment, or the moment of resistance? That is 0.36 XU max by D 1 minus 0.42 XU max by D to FCK BD square. Okay, so in our problem we will use M20 grade of concrete and Fe415 grade of steel. So my FCK value is 20 Newton per mm square and Fy value is 415 Newton per mm square. So what is the corresponding value of XU max by D for so this value XU max by D, it depends upon the grade of steel. As per the code, it depends upon the grade of steel. Okay, so what is the value? It is 0.48, 0.48, or you can just simply write for Fe415 this XU max by D value, that is 0.48. This is as per code. Okay, so just put in the expression 0.48, 1 minus 0.42, 0.48, FCK is 20 into BD square. Okay, B is how much? B is not given, so initially you have to assume let's say width of the beam is 300 mm. Okay, so let's assume this B into D square. Okay, so mu we got 600. So 600, it is in kilonewton meter, so into 10 to the power 6, convert this into Newton mm. So this is equal to, if we calculate, that will be around 2.76 into BT square. Okay, so let's find out D. So if we calculate, it will be around 851.25 mm. Okay, so let's take 852 mm. This is the required depth, 852 mm. Now let's assume this diameter of bar to be used is 25 mm and the clear cover is equal to 25 mm. Okay. So if you take 852 mm, then what will be the overall depth? It will be D plus clear cover plus 5/2. Okay, that is equal to 852 plus 25 plus 25/2. So this is 89.5 mm, or you can take round figure 900 mm. Okay, so D provided is 900 mm. What will be small d provided now? It will change little bit. 900 minus clear cover minus diameter of the bar by 2. This is 862.5 mm. Okay. 862.5 mm. Now we will calculate the area of steel. Area of steel to resist a bending moment of 600 kilonewton meter. So obviously we will design by considering it as a under reinforced section, because that will be safe. 0.87 FYSTD 1 minus FYST divided by FCK BD. Okay. So this is 600 into 10 to the power 6 Newton mm. 0.87 FYST D is 862.5 into 1 minus FYST divided by FCK B we have assumed 300 mm and D is 862.5 mm. So now you can solve this. This will be a second degree quadratic equation. So after solving this equation, you will get two values of AST. One is this and another 2381 mm square. Okay, now you have to check this AST required. It should be within the minimum and maximum value as per the code. As per the code, what is AST minimum? Okay, as per the code, your AST minimum is, refer this code. This is given in clause number 26.5. This is .87 divided by Fy into BD. Okay, so after calculating, you will get 542.43 mm square. Now what is ST maximum? 0.04 pt, that is equal to 10800 mm. So we will take this value. It's coming within this range. So my ST is within ST minimum and ST maximum. Okay, so what will be, you can calculate the number of bars now. Number of bars required, that is ST divided by area of a single bar, that is 2381 is the required, and area of a single bar we have taken a diameter of 25, so pi by 4 into d square. So this is coming around 4.85. So let's provide 5 number of 25 mm dia bars. So how to provide this? Draw the section. So this is 900 overall depth, and this one you have taken 300. So you have to provide 5 25 dia bars. So this will be the effective depth. How much? 862.5 mm. So this is the cross section of the beam. Okay. So to register flexure, we have to provide 5 number of 25 mm dia bars. This is the cross sectional view. So you have to provide 5 number of 25 mm dia bars along the length of the member. Okay. So now come to design for shear. So to design this beam to resist shear, first we have to calculate the nominal shear stress, then we'll find the shear strength or the design shear strength or the shear strength of concrete. Then we'll decide whether we need to provide the shear reinforcement or not. Okay. So let's calculate what will be the nominal shear stress. As per code, this is denoted as tau v, which is equal to vu by vd, which is equal to vu by vd. So this is equal to, first we need to find out the nominal shear force, that is vu, nominal shear force. So this is a simply supported beam. Okay, so if you draw the shear force diagram, it will be like this. So as you know, at the support we'll have the maximum shear force. So we have to calculate this shear force at the support, and we'll take that value to design. So if this is W, then this will be, this is L, this one will be W into L by 2. Okay, so VU will be WU into L by 2, and or you can simply write WL by 2 into 1.5. The factor value will get, this is 50, L is 8, so this is coming 300 kilonewton. Now what will be tau v, vu divided by vd. B is 300 mm and d is 862.5. 862.5, or we can just take it as 850. That is equal to 1.18 Newton per mm square. Okay. Now we'll find out the maximum value of design shear stress, that is tau C max, which is equal to, so you have to refer table number 20 of IS 456, which depends upon the grade of concrete. Okay, so for FCK value of 20 Newton per mm square, what is the corresponding value of tau C max? That you can get from table number 20. So this is 2.8 Newton per mm square. Okay, now we will check whether this, as per the code, we have to check first whether this nominal shear stress value is greater than tau C max or it is more than tau C max. So this is less than tau C max, so this is okay. If it is more than tau C max, then we have to redesign the member. Okay, now we will calculate tau C. From table number 19 of IS 456, which depends upon the percentage of steel and the grade of concrete. So for FCK 20 Newton per mm square, and the percentage of steel, that is denoted as PT, that you can calculate ST by BT into 100. How much ST we have provided? So we have provided 5 number of 25 mm dia bars divided by 300 into 850 into 100. So this is coming 0.96%. So for PT value of 0.96 and FCK 20 Newton per mm square, we have to find this tau C value from table number 19 of IS 456. Okay, so what is the value from table number 19? Okay, we can refer the table. Okay, so you can see this is IS 456 table number 19. This is for design shear strength of concrete. design shear strength of concrete, that depends upon the percentage of steel and grade of concrete. So we are using M20 grade of concrete. Percentage of steel we have calculated 0.96. So 0.96 means between these two values it will be the corresponding value is between these two. Okay, so for 0.75 this is 0.56, for 1 this is 0.62. okay, so what will be the value for 0.96? So it will be somewhere here. So that we have to calculate by doing linear interpolation. Okay, means what is the difference here? 0.25, and what is the difference here? This is 0.06. okay, so for 1 what will be the difference? 0.06 divided by 0.25. okay, so for how much we require? 0.96. so 0.96 minus 0.75, that will be how much? 0.75, 0.85, 0.95, 0.21. 0.06 divided by 0.25 into 0.21 for 0.2. This is the value. So what will be the value for 0.96? For 0.96 will be for 0.75 it is 0.56. 0.56. So this plus this value, so this is x, so this plus x. So if we calculate, it will be around 0.61. so this x value if we calculate, it will be 0.05. just add this value to the corresponding value of 0.56, so you will get 0.61. okay, so this value will be 0.61. Newton per mm square. Now we will check whether your shear reinforcement is required, design shear reinforcement is required or not. okay, so what is the meaning of this? Design shear strength of concrete, that means this much amount of shear can be resisted by the concrete present in the beam. okay, but how much amount of shear is from the external side, that is tau v, we have calculated 0.18 Newton per mm square, which is more than the your shear carrying capacity of concrete, which is 0.61. so here tau v is more than tau c, so concrete cannot take all the shear stress here. that means we have to provide the shear, we have to design for shear reinforcement for how much amount? The rest amount. so here this is 1.18, this is 0.61. so for rest amount, that is 0.18 minus 0.61. so for this much amount we have to provide the design shear reinforcement. okay, so actually this is denoted as tau v minus tau c. as per code this is denoted as vs. okay, so if we draw the shear stress diagram, okay, this is the beam, this is a shear stress diagram. so this is your tau v 1.18, This is tau v is 1.18 Newton per mm square. So this is tau v. Okay. So if you this is the nominal shear stress diagram. So if you draw the shear stress diagram for concrete, that is taken by the concrete. So out of this, this much of shear stress is carried by concrete. So this amount is how much? 0.61. Okay. So from here to here, all the nominal shear stress is taken by the concrete. So here, this is taken by concrete. So in this region, no need to provide the design shear stress. So for this region, we can provide only the nominal reinforcement. Okay, and for rest part, this and this, we have to provide the design. We have to design for shear reinforcement. Because we know at the support shear stress is maximum, so at the support we have to design for shear reinforcement. So you can calculate this length for how much we will provide nominal and for how much we will provide this design shear. From similarity of triangle we can calculate this. Okay, so let's consider this two triangle. This is one triangle and this is another triangle. Okay. So from this two triangle I can write here 1.18 minus 0.61 divided by, let's say this is x. X is equal to 1.18 divided by, this is how much? Total length is 4, so this total length is 8, this will be 4 meter by 4. So you can calculate this x value, it will be around 1.93 meter. So this is 1.93, this is 1.93. So this rest part is 8 minus 2 times 1.93. So this is equal to 4.14. Okay, so we'll calculate separately for nominal and for design. So as per IS 456 clause number 26.5.1.6, you can check this. What is the expression? ASB by BSV should be more than equal to 0.4 divided by 0.87 FY. Okay, so here what is ASB? ASB is the area of the stirrup that will provide to resist shear. Okay, and AB is the width and SP is the distance between the stirrups, that is the spacing between the stirrups. Okay, so here we have two unknowns, ASB and SP. So we have to assume one. So we'll assume this area of the stirrup. Okay, so let's assume this 10 mm dia 2-legged vertical stirrups. What will be the area? 2 legs are there, so we have to multiply 2. So this is coming around 157 mm square. So from this expression you can find the spacing ASP, that is equal to ASP 0.7 into Fy divided by 0.4 into B, that is 300. So this is coming 472.3 mm. 472.3 mm. Now as per the code, there is some spacing criteria. As per clause number 26.5.1.5, the spacing should not be more than, or you can say the maximum spacing should be, okay, you just write the spacing should not be more than number 1, what we have calculated from this expression, that is 472.3 mm. Second, 0.75 D, that is 0.75 into 850, that is equal to 637.5 mm. And number 3, it should be less than 300 mm. So out of this 3, this is minimum, this is the minimum value, so you have to consider that. So provide 10 mm dia 2-legged stirrups, or you can say vertical stirrups, at a rate of 300 mm center to center spacing as nominal shear reinforcement, that is for a length of 4.14 meter. Okay, so next for rest part we'll calculate what will be the spacing, that is your design shear reinforcement. So this is your nominal shear reinforcement and this is your design shear reinforcement. So as per clause number 40.4, what is the expression? This is an expression given, VUS is equal to tau V minus tau C into BD. Okay, so this is 1.18 minus 0.61 into 300 into 850, so this is equal to 145.35 kilonewton. There is another expression, VUS is equal to 0.87 FYSVD divided by SV. So from here you can find the spacing, 145.35. This is in kilonewton, so convert this into newton. 0.87, this is 415. ASB we have calculated 157, D is 850 divided by SV is the unknown here. So from this you can get this SP value, which is equal to 331.49 mm. Now as per the code, this value should be less than 0.75 D, it should be less than 300 mm, it should be less than 331.49 mm. So out of this, what will be the SP? This is 300 mm. So here also the spacing is coming 300. So let's provide 10 mm 2-legged vertical stirrups at a rate of 300 mm center to center for a distance of 1.93 meter from the support at both the ends. Okay, so finally we have to draw the figure. you have to show all the detailing. So let's say this is the support. Okay, so there will be longitudinal reinforcement, 5 number of longitudinal reinforcement. If you draw the cross section, you can see 2, 3, 4, 5. Okay, so this is 300, this is 900, this is 5 number of 25 mm dia bars. Okay, now we have to provide the stirrup. To hold the stirrup, we have to provide 2 hanger bars at the top. Okay, so at the top we have to provide 2 hanger bars. Of diameter, let's say 2 12 mm dia bars is hanger bars. Okay, so this is the longitudinal reinforcement. Again, as per clause number 26.5.1.3, if the depth of the beam is more than 750 mm, we have to provide side face reinforcement of area 0.1% of the wave area, which is equal to 0.1% of 300 into 850. This is coming 255 mm square. So if you provide 10 mm dia bar, if you provide 10 mm dia bar, it's side face reinforcement, assuming 10 mm dia bar. What is the number of bar? 255 divided by pi by 4 into t square. So it will be around 3 point something. So let's take 4 number that we have to distribute equally on both the faces like this. Okay, we have to distribute equally on these faces. So this is 4 10 mm dia bar as side face reinforcement. Okay, and last is the stirrup. Vertical stirrup we are providing. So here we got equal spacing both for nominal and design shear. Okay, so you have to show all the detailing. These are 525 dia bars. This is the longitudinal reinforcement. Then there will be 2 12 mm dia hanger bar. Then the stirrup, the spacing is 2-legged 10 mm 300 mm center to center. Okay, and what is this total length? Length is that we have to show here 8 meter. Effective depth is given 8 meter. Okay, here the overall depth 900, this is 300. So everything, every detailing we have to show here. Okay.